Inverses of trigonometric functions. We've done inverses before, right? We did it back in chapter 7 when we were doing exponential functions to get logarithms. And we did it in chapter 9 when we were just working with finding inverses for linear and quadratic and cubic functions. So we're basically going to be doing this very similar thing to what we did then. Okay? It's just we're talking about trig functions now instead. So here's the thing. So here's the functions, and we'll think of them this way. Okay? I've got sine, cosine, and tangent here. And so if I take the sine of an angle, I get a ratio. Okay? Sine of 30 is 1/2. Sine of 60 is square root of 3/2. Okay? So I have theta in this case then. The angle is my independent variable, okay? My x basically. And a, the ratio I get, is my y, or my dependent variable. So when I do the inverses, what happens? Those things switch. What became my, or what was my dependent, a, is now my independent variable. Okay? Y became x, x became y. And theta is now going to be my independent, what I get when I'm doing inverses. Okay? So what do we say when we're talking about inverses? It's a reflection over the line, y equals x. So the values of x and y switch. So in this case, basically we're talking about our angles are x, which give us the domain. The ratios a is y, which gives us the range. And when we go from the function to the inverse, then those things switch. Now when we're talking about trigonometric functions, the inverses themselves are not functions. Okay? The reason is because trigonometric functions go on and on and on forever, okay, horizontally. They just keep going. So let's take a look at the graph of sine for a moment so we can see that. Here's the graph of sine. If we took those values off from the unit circle and plotted them, we would get this graph. It looks just like this. This graph goes on and on and on. So here's a graph of sine. Why is the inverse of this not a function? We had a specific test we looked for to see if a function, okay, the horizontal line test, it fails the horizontal line test, right? Okay, so the inverse of this is not a function. So we're actually, one of the things that we did back in that is we looked a little bit at restricting functions so that their inverse was a function. And we're actually going to do that more with these. Okay, there's the graph of sine. Graph of cosine looks very similar to it. Okay. But it's not, the inverse of that would not be a function either. Would fail the horizontal line test. So the inverse of the trigonometric functions are not functions themselves because there are many values for theta for a particular value of a. Okay. Coterminal angles, right? We found out in that example, or the warm-up, that cosine of 570 is the same as the cosine of 210. So there's two x values with the same y value, so they can't be inverses. All right. Here it talks about, for instance, suppose that you want to find the inverse cosine of 1/2. Okay. Let's say we're just looking at unit circle. Inverse cosine of 1/2, the answer could be at pi/3, or it could be at 5 pi/3. Both of those are options. So what we're going to do is we're going to look at two different things. Okay? We're going to look at finding all possible values where it's true. And then we're going to look at the actual function for the inverses. And so we're going to do some restrictions. So make sure you have your unit circle out. Like I said, you're always going to need to have that out. Okay. So finding trigonometric inverses. Now, there's two ways we're going to look at this. Okay? And the thing is that you have to read what it says more often than not. So right now, this says to find all possible values. That means everyone there could ever be. Okay? And when we say that, we're going to focus on the size of this letter here. Okay? That's a lowercase c for cosine. Okay? Because we're going to look at them situations where it's lowercase and when it's uppercase. So when we find all the possible values where inverse cosine square root of 3 over 2, we want to look at our unit circle and find out where does cosine equal square root of 3 over 2. Okay? So reminder, cosine is x. So if you look around the unit circle, where do you see that the x value is square root of 3 over 2? Okay? At 330, except we're going to be dealing with radians. Okay? So at 11 pi over 6, and at, where else? X is square root of 3 over 2 here. Where else? When we're talking about cosine, we're talking about x, right? So x is positive. So since x is positive, we know it's got to be on the right-hand side of the y-axis. Right? So we get 11 pi over 6. So it's here at 11 pi over 6. We get positive square root of 3 over 2. And at pi over 6, right? Okay. So I will write down then pi over 6 and 11 pi over 6. Okay, to start with. All right, so there's our first step. Okay. Step 2 then says find the angles that are coterminal with those angles. Okay. Well, what are all the angles that are coterminal with those angles? Okay. So if I have pi over 6, every time I go around the circle again and I stop there, I'm at pi over 6 again, right? Okay. And I go around it again, I'm still at that same spot, aren't I? So what am I doing to go back around to get to that spot again? Because this would be pi over 6. If I went all the way around again, it would be at 13 pi over 6, and then 25 pi over 6, and then 37 pi over 6, and so on. Or I could go the negative. What are we doing? I'm adding 2 pi. Okay? And if I'm at 11 pi over 6, okay, to go around the circle and end up back at 11 pi over 6, I'm going to add 2 pi. Could I go negative also? Yes, I could. So what we're going to say then is the fact that this would be 11 pi over 6 plus 2 pi, and we're going to use the letter n here. And then we're going to say where n is an integer. Okay. What are integers? What are integers? I guess so. Integers are positive and negative whole numbers. So this means that I could be going clockwise or I could go counterclockwise, multiples of 2 pi. So my answer to this problem is pi over 6 plus 2 pi n. 11 pi over 6 plus 2 pi n, where n is an integer. Okay? Because we're talking about all possible values. That means every time it could stop on that unit circle, or we're talking about if we put square root of 3 over 2 and y2 here, we're talking about all the times that it intersects that graph. Okay. Letter B, find all possible values. All right, we're going to work with cosine again, where cosine equals negative 1/2. Now, the signs are very important. Okay? Negative 1/2. Cosine is x, right? And x is negative where? On the right or left side of the y-axis? On the left side. Okay? So that means then that all I need to do is look over here on the left side, say, okay, where is the x value equal to negative 1/2? Because we're talking about cosine. Cosine is x. It's negative on the left side. So where over there is it equal to negative 1/2? No. Okay. Happens down here in the third quadrant at 4 pi over 3. And where else? Okay. Up here in the second quadrant at 2 pi over 3. So my answer will be 2 pi over 3 plus 2 pi n and 4 pi over 3 plus 2 pi n. And yes, you always have to say this, where n is an integer. So do you want to, when we're doing these problems, utilizing the fact that, and I don't have it on this one, but the fact that we wrote down that these are, with cosine, sine, tangent, it's also plus, plus, plus in the first quadrant, and negative, positive, and then tangent is negative in the second. X and y are negative in the third, so tangent would be positive. And then the fourth, tangent's positive, or cosine's positive, sine negative, tangent negative. So when we're talking about, if you're talking about sine, then okay, where's y negative? If we're talking about tangent, then we're talking about the other one. When is the one on the outside negative? So speaking of tangent, there you go. Find all possible values where the inverse tangent, or of the inverse tangent of 1. So here's our answer for inverse tangent of 1, pi over 4 plus 2 pi n, or 5 pi over 4 plus 2 pi n. But the question is, could I have used one response instead of two to answer this question? Okay. And what I want you to think about is look at the unit circle. Okay. Look at tangent in the first quadrant and the third quadrant. They're both positive there, right? Tangent in the second and the fourth are both negative. So here's pi over 4. Here's pi over 4, our answer. And the other answer was 5 pi over 4, right? Okay. And I would end up back here at pi over 4 again, wouldn't I? And then back down here to 5 pi over 4. And how much do these differ by? 180 if we're talking about degrees, or pi if we're talking about radians, right? Okay, let's look at another one. All right, let's take 2 pi over 3, for instance. Tangent's negative square root of 3 there, right? Okay. If I go pi radians, that means I'm coming over here to 5 pi over 3, right? And tangent is negative square root of 3. Now, does that work with sine and cosine? No, it doesn't, because sine and cosine are either positive on the right side or positive in the top. Okay? But it works for tangent, that with tangent only, you could respond by saying that I could put pi over 4 plus pi n instead of 2 pi n. Okay? Do you have to? No. I'm just saying that you could. Okay? Just wanted you to think about that. Okay? For tangent, because all those tangents, they differ by pi. And something that we'll talk about later on, and when you take pre-calculus, we'll talk about it. We're actually talking about it right now with pre-calculus class, that we have something that's the the graphs of sine, cosine, or tangent, they're what we call periodic graphs. Okay? Basically, that just means that they repeat themselves over and over and over again. Okay? Sine and cosine repeat themselves every 2 pi, which is why we're using 2 pi n there. And tangent repeats itself every pi. That's why we could use pi n for tangent and not for sine and cosine. All right. Now, with that being said, okay, for us to be able to make the inverses of sine, cosine, and tangent into functions, we have to restrict their domain. Okay? And so we have to restrict their domain so that it involves all possible values, so positive and negative ones. So because more than one value of theta produces the same output value for a given trig function, it's necessary to restrict the domain of each trigonometric function in order to define the inverse trigonometric functions. Trigonometric functions with restricted domains are indicated with, here's what I said, we're going to look at this. There we go. Capital letters. Okay. So if we're using capital letters, that means we're restricting the domain and range. In the problems we just did, okay, we used lowercase letters, said let's find all possible. When we use uppercase letters, we're going to use restricted values. Sine is going to be restricted to the fourth quadrant and the first quadrant, okay, where because y is negative here, y is positive there. We got to be able to incorporate all positive and negative values. Cosine is restricted in the first and second quadrants from 0 to pi because we have positive here, negative values here for x. Tangent is also in the fourth and the first because there I get both positive and negative values. Now the question might be with tangent, it's a little bit different. Question might be, okay, why not have tangent go from 0 to pi? Because tangent's also negative in the second quadrant, right? The difference is that it's not continuous there, okay? Because if you look on your unit circle, what's tangent at 90 degrees or at pi over 2? It's undefined, okay? So we have an asymptote there, so the graph would have a break in it, where at 0, it's equal to 0, so the graph would be continuous. Okay? So these functions can be used to define the inverse trig functions for each value of a in the domain. There's only one value of theta then. Okay, so we're looking, there's only one possible answer. And so what this is going to cause us to do then is we're going to have to do a little tweaking to our unit circle. Okay? Just a little tweak to it. All right, so here we have this inverse trig functions, here's a chart thing. That we'll be looking at. Inverse sine. Okay. So we're switching, remember when we're doing inverses, we're switching the ratio and the angle. So if it says inverse sine, that means we're doing inverse sine of a ratio. That ratio has to be between -1 and 1. And then the angle that I'll get from that has to be between -pi/2 and pi/2, or -90 and 90. Okay? Has to be something that's on the right-hand side of the graph of our unit circle. Cosine, okay, of A, of the ratio, inverse cosine of the ratio, that also has to be between -1 and 1. And we'll actually explore with our calculator a little bit as we're doing this. And that's going to be in the upper half of the unit circle, from 0 to pi or 0 to 180. Inverse tangent, my domain, and they put from -infinity to infinity, but what does that entail? What numbers are from -infinity to infinity? Everything. So instead of putting that, I could put all real numbers, yep. So this could be all real numbers here. And then my response, my angle I'm going to get is going to be between -pi/2 and pi/2, or -90 and 90. Now, one thing to notice. With sine, it includes -90 and 90. With tangent, it does not include them because they're undefined there. Okay, you have asymptotes. So I said we're gonna work with our unit circle a little bit, right? We're gonna do a little tweaking to it. Here's what we're gonna tweak. Okay, because sine and tangent are in the third and fourth quadrant, but it says the answers I have to have are between -90 and 90, or -pi/2 and pi/2. That means that when I look at my unit circle, and I'm looking at the fourth quadrant, these numbers in the fourth quadrant are between 3pi/2 and 2pi, or between 270 and 360. The difference is that I have to look at if I'm going clockwise. Which, if I'm going clockwise, those angles are now what? Instead of them being positive, they have to be negative. Okay? Which means that 11pi/6, that's the same as -pi/6. 7pi/4 is the same as -pi/4. 5pi/3 would be the same as -pi/3. Or instead of 330, we're talking about -30 and -45 and -60. Okay? So we also have to think about this fourth quadrant, these numbers, when we're talking about the inverse trig functions. These numbers have to be our negative angles, because we're going to go clockwise instead of counterclockwise. Now, take out your calculator, and we're gonna work with this, and I'm going to show you why this is true. Okay, let's make sure we're in degrees, because we understand that just a little bit better. So I'll check my mode here, and I am in degrees. Okay, so that's good. Okay, so I want you to do inverse sine. We'll just do the easy one first of all, of 1/2. Okay, when does sine equal 1/2? At 30 degrees, right? Okay, so if I do inverse sine of 1/2, I should get 30 degrees. Okay, and we do. Okay. Now, if we change it to -1/2, okay, there's actually two possible answers I could get. Or, well, actually, because sine is equal to negative 1/2 at 7 pi over 6 or at 210, but it's also equal to negative 1/2 at 330. But if I put this in my calculator and hit enter, then I get negative 30. Because your calculator is actually going to give you the right quadrant, and it'll give you the negative value. Okay? Because the calculator understands that if I'm calculating the inverse sine of negative 0.5, that means that my answer has to be between negative pi over 2 and pi over 2. Okay? Or negative 90 and 90. Right? Let's try cosine. Right. Cosine of a negative, we said here, has to be in the second quadrant. That means that my answer I get when I do inverse cosine of a negative has to be between 90 and 180 degrees. Okay. So if I use my calculator for a negative cosine, so let's do cosine of negative 0.5. Okay. Cosine of negative 0.5 should be at 120 degrees then. And your calculator will tell you that. Okay. Oh, that's because anybody know why it messed up? I didn't do the inverse, that's right. Okay. Inverse cosine of negative 0.5 would be 120 degrees. Okay. So it'll give you the right value there. Okay. But you need to be able to look at here and find it without. Okay. All right. So when we're talking about restricted ones, and here's the difference, okay? This says evaluate each inverse trigonometric function, give your answer in both radians and degrees, okay? Both radians and degrees. And this is a capital letter. So that means they're not trying to find all of them. That means we have to work with that restricted domain. So we're doing inverse cosine negative square root of 3 over 2. That means my answer has to be between 0 and 180 if I'm talking about degrees, or 0 and pi if we're talking about radians for inverse cosine. So cosine is negative. Between 0 and 180, 0 and pi, where's cosine negative? Which quadrant, first or second? Second, because x is negative in second, okay? So where does cosine equal negative square root of 3 over 2? In degrees, it's what? 150, yeah. And in radians, it's 5 pi over 6. So if it says capital letter inverse cosine, that means I'm looking just from 0 to 180, 0 to pi. Cosine is x. It's negative square root of 3 over 2 at 5 pi over 6, or 150 degrees. Sine of 3/2. Sine is between negative 90 and 90, or negative pi over 2 and pi over 2. It's 3/2 on the unit circle, first of all. That's not a number we have on the unit circle, is it? Okay. So let's take our calculator and do the inverse sine of 3/2. What'd you get? An error. Okay. Did you get an error too, Jenny? Okay. All right. Did you know why it's an error? Because it's wrong. Okay. All right. Because this says if we're doing inverse sine of A, that value of A has to be between -1 and +1. And 3/2 is greater than 1. So there is no value where sine is equal to 3/2. So this would be, there's no solution to this.